Right, so this is my talk on grappling with infinity, high precision math in Rakudo. The reason behind this, what's the problem? So we have these wonderful things called rats. They're rational data types, numerator, denominator, wonderful things, except they fall back to num, which is entirely reasonable. It's just it doesn't play well how this is written. So Rakudo provides a fat rat. This does not fall back to num. So we have fat rats are nice, and except when they do, they can still fall back. And yeah, this here, 39 years to compute, not really practical. To be fair, I am kind of abusing rationals here, and the denominator on this is exploding towards infinity exponentially. So, yeah, we've kind of got a problem here. This is my ideal numeric data type. No downgrades ever. Needs to be fast-ish for some definition of fast. And we need to be able to specify our precision and guarantee that we can meet that precision. And I'm currently calling these things trim rats. So, the guaranteed minimum precision. So precision is sticky. That is, how we can do this is you can either do a light version of symbolic math internally, where you basically store the op tree of everything that has happened to that variable, or you can use guard digits. I call them scorched earth digits because guard digits has a very different meaning under IEEE floating point math internally for the IEEE spec. Scorched earth digits is what Math Big Float uses. They internally compute far more than what you actually specified the precision at. And then how this plays with different precision types, determining min versus max on that. And this last point here blends into algorithm choice, but I've stuck it here because the algorithm choice impacts precision because addition and multiplication don't generally lose precision, but subtraction and division do. But I'm not too terribly concerned about division because of our choice of using basically the rational roll type, we are able to convert division into a multiplication of an inverse. It works out in our favor in that regard. So symbolic light and math and guard digits. Math Big Float ostensibly uses them because, well, they are genuinely easier. They have their issues. If you do a lot of math on them, your error builds up and propagates into the actual precision chunk. Whereas if we're doing an internal op tree where we store internally on each variable all the operations done on that variable as well as what they were done against, we can then, if need be, go back and recompute the entire tree up to that point and guarantee that if you specified 30 digits of precision, we are going to deliver 30 digits of precision at that point. That can get a little expensive though. So back to how do you choose if you have a precision mismatch. Let's say you have one term rat at 20 precision, 20 digits of precision after the decimal place, and another at 30. Which one do you choose? Nearly always min. Like I said, down here on the bottom, max is only correct if we can go back and recompute. There would be cases where even if you did have the internal op tree, you would not be able to go back and recompute, and you'd be forced into using min.
So if you were to take max and cannot recalculate everything, it would kind of look like you have 30 digits of precision.
Precisely, yes.
Only really get 20.
That's exactly what would happen. And you're trying to minimize error propagation into your actual precision amount. That's why you choose min. Yes?
Maybe you could have like two precisions, one that is what you trust and one that is what you have. And then intermediate results are more precise than end results. So in the end you have to go to what you trust, but intermediately you like to be much more precise.
Where that breaks down is, let's say you have, let's say you have a trust value of 20 digits of precision and your intermediates are out to 30. And all 10 of those intermediate digits are 9999999. And you then round, and then you do math on that, and that's going to then take that garbage out here and propagate it into what you trust. And now your last digit of what you trust is not trustable anymore.
I know.
Yeah.
It's weird, complicated.
Yes. Yeah. So fast-ish. Because this is I'm currently doing this in pure Perl. Fast is a little relative. I would eventually like to get to where I get the hot points down into C. Proof of concept, making sure I have it correct. I want to do it in Perl first. So fast enough, part one. Yeah, my point exactly. First be correct, then be fast. And for the love of everything holy, do not repeat the mistakes in Math Big Float. There was relatively recently a span of several years where several of the trigonometric functions didn't actually return what they should have. One of them returned correct values within a very specific range and then just fell on its face outside that. Another one, it was effectively acting like a pseudorandom number generator, and it was kind of indeterminate what was coming out of it. This all leads into my last point on this slide: test everything. This is an ideal situation for test-driven development. We have a well-defined interface. In my case, trim rats are being designed and written to be a drop-in replacement for rationals. So my interface is everything that Perl 6 specifies. And because this is math, we have very well-known output for millennia. So we have the beginning and the end, and we just have to write the test that verifies that the black box in the middle is doing what we expect.
And every test looks like input, output.
Yeah, yeah.
No setup or...
Yeah, it should be a relatively easy test to write. It's just, we need to test this. Particularly because algorithm choice is a bit interesting. An example I have is if you're trying to do, in my case, I was trying to do square root. I knew Newton's method had quadratic, it's, what do you call it? Sorry, it's giving me a hint. Not that one. Newton's method will double the number of digits of precision for each iteration if it works. Which is why it's just no. I've coded it up and it just fell flat on its face for the vast majority of tests I did. You have to be incredibly careful with how you use Newton's method. Brent's method is better. It actually takes three different basic, I'm using the wrong terms here, but basically goalpost methods where you have very solid guarantees that this is below your 0 point and this is above your 0 point. And then it iterates in towards your 0 very nicely. Yes?
I think there's one that you learn in school 100 years ago, how to do square roots like you divide manually.
Yes.
And this method you can transform to base 2 to some power or to base 2, and it works quite neatly and
Yes.
quite fast.
Yeah, you're that's either bisection or that's going to be false position. Brent's method uses both of those as as its fallbacks. Its primary driver is a secant method that does some other stuff. And then bisection, it's not great, but it is very consistent. You will get a convergence of 1. It will converge, guaranteed. It may take a while getting there. Heavily prefer simplicity because of both maintainability and being able to educate other developers coming in to progress the module. So this is why you don't want to be using Newton's method. If you want, I can break down the math. But in the end, you have to be sufficiently close to the root that you don't know before it will have any guarantee of convergence. And even if you get there are the issues that are on the next slide. So the TLDRs, it is trivial to get Newton's method to not converge. Newton's method is great in an academic setting where the teacher can set up a situation where it does converge. In the general world, you get this. This is a Newton fractal. Yes?
It looks very nice.
It's very pretty. However, notice these red blobs. Those red blobs are the first 2 points there where you either have a stationary iteration point or the iteration point is a part of a cycle. It will never converge to a root.
But it still looks like.
It's very pretty. It's completely and utterly useless for a math module. And so here's Brent's method. The key takeaway here is this last one. That n of the n squared is defined as the number of steps that bisection would have had to have taken. So when it falls down hard.
Oh, yes.
So yeah, super simple, not great, but it gets you there. And it's sort of kind of trivially parallelizable. That idea I took from Ralph Holtz and his parallel get bisect. It works-ish, but at all the attempts I've done, the overhead of setting it up swamped any performance gains I got. So no data type downgrades ever. This means we're doing arbitrary precision algorithms. Yes, we specify a precision for a given data type or for a given variable, but that means that our algorithms underneath us have to be able to take anything. This is the stuff that needs to happen to make sure that no downgrade can become a thing.
Does that mean you support big integers for the precision count?
Yes.
Whoa. Do it.
It means, but if you really want to do that, your denominator really does explode towards infinity and your machine slows down a lot.
Yeah.
You can do it, but it's not
It might
advanced.
be a bit of a memory issue.
Yes, there's that too.
Yeah.
So bisection covers a lot of this stuff. Binary explanation is really awesome. It allows you to do very large exponentiations very quickly. And then for rational powers in between all the integers, you can do this. This is based off of the fact that the ratio, so if you have an integer and an integer, the midpoint, the 0.5 in the middle, that ratio between beginning and midpoint and end is always going to be 1 over the square root of whatever your base is. So doing math and simplifying it out, you get to this. It's nice, it does bisection for rational powers, however it's not parallelizable because it is truly iterative. You end up using the results of the previous step in the next one. This is my first attempt at logarithms. It works, but oh boy is it glacial. So later I have something else that I'm going to try, but I haven't gotten around to it yet. This TinyMT, great for just general everyday use, but this is about being correct, then being fast. And if we just simply take TinyMT and try beefing it up to the number of digits of precision that we're expecting, either one of these two is next points is going to hit where you're either going to be spreading 64 bits of precision across 256 bits of precision, and it doesn't scale well. You're going to end up introducing significant non-randomness. In essence, entire numbers are going to be skipped. And you'll never be able to actually select them. So my proposed idea is basically use a block cipher to seed your initial counter value and then the increment to that counter value, and then use a stream cipher to then basically encrypt the counter, the value of a counter, and just stream that out as much as you need. I need to implement it, see how well it's going to work. At least on paper, it looks nice. We'll see how well that goes. All the trigonometric functions. This is where I basically intend to spend one of my technology tokens. Most people use Taylor polynomials. Chebyshev polynomials get you there 1 to 2 iterations faster. But they're significantly less well documented, which is why that's where I'm spending the technology token on this project. Not quite sure what I'm going to be doing about inverses yet. Hyperbolics are easy, they're just ratios of E. Same with inverse hyperbolics, it's just inverse of that and you get natural logarithms. So, constants. Janovsky algorithm is awesome, it is crazy fast. Yes, the math looks big and scary, but that thing converges amazingly well. Yeah, even that E specification there, while non-standard, does work reasonably well from what I've tested. And now for the generalized continued fractions. I'm planning on using these for the hyperbolic trigonometric functions because, well, we have E, it works, and the nice thing about these is your error term is wherever you cut off, the next term after what you cut off. It makes it really easy to know when to stop. And this is what I'm intending on testing out for natural logarithms instead of what I showed earlier. Hopefully it converges reasonably well because of this next slide. This is linear convergence for pi. Janovsky just blows this out of the water. So while it's mathematically elegant, not really practical for real-world use. And then data type upgrades. Int and rational are really easy. You just throw them in the appropriate sections. We actually need an error or epsilon term for converting nums, which I've got working. It's not great because at the moment I'm just simply chopping stuff off and not rounding to the nearest rational fraction, which would be the better way to do this. And complex numbers actually do need to happen because those trigonometric functions, you either dip directly into the imaginary plane and then back out again to get real numbers, or you just simply end up in the imaginary plane if you give it the right values. In conclusion, this is what I'm in the process of doing. No data type downgrades ever. This means we need to upgrade data types instead of do the downgrade that is typical for the current rational data types. And to make this all happen, we need arbitrary precision algorithms for everything. It needs to be fast, but be correct first. And heavily prefer simplicity to make it easier to maintain as well as bring new people into the project. And guaranteed minimum precision, probably going to go with the internal off tree, maybe with a few guard digits just to help make sure that it's doing the right thing and make sure that precision is sticky in the direction that it should be. That is, that you're typically choosing min unless you have the capability of going out to maximum. Questions? Sorry, I've kind of sped through this.
What are you going to use this for?
My original, where I started out with all this was, I was doing simulations and I was using rats and they kept blowing up because they hit num. I went, okay, fine, we'll use fat rats. That went fine all the way up until I hit trigonometric functions and went, right, I need my own data type. And so I don't actually need to have arbitrary precision like what fat rats do. I just need to have about 30-ish digits of precision, which is more than what num can give me, but yes.
And you have like issues, what kind of rounding? So there's about 30 different ways of rounding.
Yes.
And which one do you choose, or how do you control which one of them?
That is something that I'm still not quite sure of. I am probably going to go with either random or round to even.
Okay.
I admit that I need to have some form of user configurability there.
Because I have written a library somewhat similar to that for another language, so there's a lot of issues that we can talk about.
Yeah.
Yeah.
Yeah. There's a lot of yes.
Oh, sorry, I didn't want to interrupt. I just wanted to ask, have you considered maybe quadruple or octuple floating point? I think maybe x64 supports them on some.
I have,
platforms.
but I haven't been able to get that to compile too terribly well on my machine. Which is why I'm trying to do this pure Perl.
There's this GNU multi-precision library, which looks, at least on the internet, quite interesting. And there's even a wrapper that you can make intervals around it. And if you kind of do bindings for that, is that something that you have thought about?
I have not thought about that because the main reason I have not thought about that too terribly deeply is there's two things here. One is I'm coming at this from an amateur hobbyist perspective. This is a little bit about me teaching myself numerical analysis and a lot about I want to have this be pure Perl so that it is deployable as broadly as possible. Those are my two reasons why I'm not yet going that direction. Like I mentioned earlier, I do have the intention of eventually getting it to where the pain points are in low level C, and I, for that, will almost certainly do bindings into that for those. Sorry.
But there's another issue. You have like two paths to go. One is that you kind of go this floating point, and you extend floating point to have more digits. And the other one is what the people for like banking applications, for example, they have like a long decimal or big decimal, where you have like a fraction, and the denominator is a power of 10. And they both have their justifications. And which of the paths did you follow?
This is going to be more down the fractions path, except I'm not doing it over powers of 10.
So
It's going to be more down the fractions path because I'm already basically laying on top of the rational data type inside Perl 6. What I'm doing differently than just base powers of 10 is I'm trying to find the nearest rational fraction to the round-off point. Did that make sense?
yeah,
Okay.
then the continuous fractions are very good because
Yes.
they lead you exactly there.
Yeah. Yes?
How does your type fit into the type hierarchy? Is it a subtype of rat? Or something
It is. What do I have? It's either a subtype of rat or I compose rational into it. No, it's a subtype of fat rat, and yeah, subtype of fat rat. That's what I did with it so far. Which means I am limited by what's above me in that regard.
So if it limits you, why did you do it? Why not just make it a numerical, for example?
Because I liked the concept of using the rational data type numerator or denominator. It made a few wins in a few places. We'll see if those wins actually ended up being worth it. Yes? Oh, time? Okay, well, that's it.